Hello everyone, welcome back. In the last video we were talking about no cloning theorem and we proved it. So this is one of the most fundamental results in quantum information, and today we will see that if this went true, then what would have been the consequences. Alright, and you can already guess from the name that if no cloning theorem were not true, then we could have done superluminal signaling. Superluminal signaling means that you could have communicated faster than light, and if that had happened, then quantum theory wouldn't make sense, right? And we should have there would have been hardly anyone in the whole world who would have believed in quantum theory anymore. But thanks to no cloning theorem, it doesn't happen. So we will try to understand this in this video. All right. So no cloning theorem was proved independently by D. Deeks and Wouters and Zurek in 1982. But until recently, we didn't discover that it was actually proved in 1970 by D. Park, but it went unnoticed. But the proof in 1982 was provoked by F. Herbert's method of superluminal communication via quantum methods. So what happened is that F. Herbert gave a proposal where we could actually communicate superluminally, which is faster than light, but there was an assumption, and that saved us. That assumption violated the no cloning principle. All right, so let's see. I don't want to give the spoiler right now. Please be with me, and you will understand by the end of this video that why this no cloning theorem is really important. All right, so let's start. So let's say that I had two persons, Alice and Bob. Okay, so let's say they are two. So they have a entangled pair of electrons, let's say 5 plus, which is in the following state: 1 by square root of 2, 0, 0, plus 1, 1. Okay, I hope it is clear from the notation that it's a 2-qubit system and they are entangled. You already know how to calculate them, right? So what happens is that there are 2 qubits. Let's say, for example, there can be 2 electrons in this 5 plus state. So what Alice does is takes one of those electrons, and Bob takes the another one. So Alice takes 1 qubit and Bob takes another, and they move away from each other, so away that like they can be in, if this is the whole universe, then the one can be at this corner and one can be at the other. That's not a problem. But the thing to notice here is that their qubits that they have are entangled. All right, so there is one more thing to notice here, which is this state can also be written in the following way. It can also be written as plus 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 minus minus. You can easily check it by yourself. You just take the matrix representation and you will check that both of them are the same. So I'm writing just the 5 plus state in 2 different bases. One is the computational basis, other is the diagonal basis. All right. So so they have taken 2 different qubits and carried it to 2 different corners of the universe. All right. Now, what Alice was, Herbert's proposal was that if they will communicate a yes or no message instantaneously. That means obviously faster than light, because there are in 2 different corners of the universe, and if they can communicate instantaneously, that would mean that it's a superluminal communication. All right. So what was the proposal? The proposal was, if Alice wants to say yes, then she will do a measurement in the 0, 1 basis. Okay, that means that whenever Alice measures and let's say it gets 0, then Bob will immediately get 0, right? And if Alice gets 1, then Bob will immediately get 1. It is clear from this state, right? But if Alice wants to say no, then she will measure in the plus minus spaces. And you can also immediately see that if Alice gets a plus, then Bob gets a plus immediately. All right. So what happens now? Do they have a instantaneous communication or no? If they can communicate instantaneously, then quantum theory doesn't make sense because you cannot communicate faster than light. All right, and now let's check. Now the fact is, what we are claiming is that they cannot do superluminal communication. And if they cannot do superluminal communication, then what the fact should be is that if yes or no, Bob's probability distribution will remain unaffected. If it gets affected, then they can communicate, right? If we can prove that that is unaffected, then we can show we have proved that they are not communicating. All right, so let's say that Bob does a measurement, right? So for Bob, if it wants outcome I, by outcome I, it can be 0 or 1 or plus or minus. So I'm using a general notation I. All right, it can choose to measure in the plus minus basis or in the 0 1 basis. So I'm just writing it in a general form, calling it I. All right, outcome I, the projection operator is pi I. Okay, now let's calculate if yes. So probability of getting I when it's yes is equal to, all right, so I will use a formula from conditional probability, and I hope it will be clear to you once I explain. All right, so probability of getting I, as you're doing, if it is yes, you will be in a 0 1 basis, right? So probability of getting 0 times probability of getting I, provided that you get 0, right? This is the formula for conditional probability, and then plus probability of getting 1, while the probability of getting I, provided that you get 1. All right, so I have used this famous formula from conditional probability, and because if it were yes, you had the probability of getting both 0 and 1, and so this is this for any general I. All right, so I can write it. Probability of getting 0 is obviously half, and probability of getting I is nothing but pi I 0, right? Because this is the probability, this is the state that you get, and the probability is the mod square of this. Okay, and if you take the mod square, you just get this number. Okay, similarly the second one is half, and you have this 1 pi I 1. Okay, Now it's a projection operator. Then for projection operators, we know that pi square is equal to pi. Then what we can say is that half should be 0, pi I 0 plus half 0 pi I, this should be a 1 pi I 1. Okay, now if you remember the formula that we will use now, that is that the inner product between A and B can be written equal to trace of BA. Right? We showed it in one of the videos before, so I hope you understand that. So you can think of this part as B like this, and this part as A like this. So what you can write is that half, you can write it trace of pi I 0 and 0. Similarly, you can write the second term as half trace pi I 1 1. Okay, you can take the factor half common, and trace is linear in when you're adding two numbers, adding two matrices. Then what I can show is that trace of pi I, I'm taking this pi I factor out and this big bracket here for the trace, and you can write it as 0 0 plus 1 1. Okay, so to be more precise, I am taking this half inside the trace, so this should be pi I 0 0 plus 1 1 by 2. Okay, so now this is the probability of getting I if it is yes. Now we will show that probability of getting I if it is no is the same as this, and if that is true, then there is no way Bob can distinguish between yes and no, because I'm doing it for a general state I. Alright, so let's check if no, and it's pretty easy. It is nothing but probability of getting I if it is no is equal to, similarly again, probability of getting the plus state, and this will be probability of getting I provided that sorry for the bracket here. Okay, so probability of getting I provided that you get the plus state, plus probability of getting minus provided that, and times probability of getting I provided you get minus. Alright, so you can easily check, this is nothing but again half, and now you will have this plus state pi I plus half minus pi I minus. Okay, now using the same steps again, what you can show, this is equal to trace of pi I, and you have this plus, and you have a minus by 2 bracket. Now you can explicitly calculate. Now we are claiming that these two are equal. Which two? This one and this one. Trace and pi I are there. So if we can show that this matrix in the middle, in the brackets, are equal, then we are done. So what we are trying, you can check it by yourself explicitly by taking the matrix representation, as you already know how to calculate that these two matrices are the same. So if these two matrices are the same, if you send a no or a yes, the probability of getting I for Bob is the same. Doesn't matter you get a yes or a no. I mean, it doesn't matter if it is a yes or a no sent by Alice. All right. So it proves that the probability distribution for Bob does not change if Alice sends a yes or a no. It doesn't matter. All right. So what would have happened? I mean, why is it related to no cloning principle? So the idea is cloning. If, I mean, we were in a state which was like this, right? So the initial state was something like this, 5 plus. So let's write it down again. So the initial state was 1 by square root of 2, 0, 0, plus 1 by square root of 2, 1, 1, right? And which was equal to 1 by square root of 2 plus 1 by square root of 2 minus minus. Okay? Now, if Alice wants to send a yes, then Bob's qubit will either collapse to 0 or 1. Okay? And if Alice wants to send a no, then Bob's qubit will collapse to either plus or minus. All right? So now, what we showed before, that if he doesn't know where it has collapsed, and if he cannot do cloning, then he doesn't have any idea which state, what was the message, right? This is what we proved. Now, what we are trying to say is that let's say that Bob can do cloning. So let me use a different color. Let's say that Alice sent a yes and it collapsed to 0 state. Okay, so then Bob's state is in this state, right? Bob's electron is in this state, or Bob's qubit is in this state. Now Bob can do cloning. Let's assume that. Then he has made like hundreds of clone of the same state, right? This is the definition of cloning. And now Bob can measure. If now Bob has a choice, Bob can either measure in the 0-1 basis or it can measure in the plus-minus basis. But if he measures in the 0-1 basis, then okay, let me use different colors now. If he measures in the 0-1 basis, then 100% of the times he will get 0, right? Because it is in the 0 state, and checking all the clones, he is sure that all of them will be 0, and he is sure that the message is yes, right? The same will go for 1, because then all of them will collapse to 1. But Bob had a choice, because he didn't know the message from before, so he could have equally chosen to measure in the plus minus basis. But if it had collapsed in the 0 state, then and he measures in the plus minus basis, then 50% of the time he would get plus, and 50% of the time he would get minus, right? Because the 0 state can be written as the linear combination of plus and minus. Okay, so if by seeing this distribution, he can definitely say that it was either 0 or 1. It was definitely not plus and minus. And then from there, he's sure that the message is yes. So it doesn't matter he chooses to measure in the 0-1 basis or in the plus minus basis, he would definitely get the message that it was yes. And the same thing goes for no. Then all of them will be, let's say, in the minus state, and then you can measure in both, and either you'll get a 100% of the same state, or you'll get a 50-50 distribution. From there you can understand the message. All right, so this is the idea of no cloning. I mean, this is how no cloning principle saves us from superluminal communication, and this is one of the fundamental results in quantum information. And if no cloning principle were not true, then quantum theory would have been in danger. All right, so I hope you understood it, and if you still have any questions, please don't hesitate to ask us during the live discussions. Thank you so much.